Welcome to another module in this massive open online course on estimation for wireless communication systems. So previously we have looked at OFDM channel estimation, that is how to transmit the pilot symbols on the various subcarriers, find the estimates of the channel coefficients in the frequency domain, and later from these estimates in the frequency domain compute the estimates of the channel taps in the time domain. Alright. So now we are going to look at a different scheme for OFDM channel estimation. This is known as a comb type pilot based OFDM channel estimation. Alright. So we are going to continue looking at OFDM channel estimation, where remember again OFDM, all of you should be familiar by now, stands for orthogonal frequency division multiplexing. We are going to look at OFDM channel estimation, and we are going to look at OFDM channel estimation using comb type pilots. So we are going to look at OFDM channel estimation using what are known as a comb type of pilot. So OFDM channel estimation using comb type pilot symbols, or we can also abbreviate this as CTP, where CTP represents a comb type pilot transmission for an OFDM system. Right. So first let us understand what is this comb type pilot and pilot transmission, and let us understand what is the motivation for comb type pilot transmission. Okay. So let us go back to our L equal to 2 tap. So let us consider our N equal to 4 subcarrier OFDM system, as we have considered previously also. N equal to 4 subcarrier OFDM system with L equal to 2 tap ISI channel, where ISI stands for inter symbol interference. All of you should be familiar with that by now. So L equal to 2 tap ISI channel. Therefore, I have Yk, which is equal to H0 times Xk plus H1 times Xk minus 1 plus Vk. What is this? This is basically your 2 tap ISI channel. H0, H1, these are your L equal to 2 taps. These are the L equal to 2 channel taps. Xk is the, again something we already seen, Xk is the current symbol. This is the previous transmitted symbol, and that is what we said. OFDM, that is orthogonal frequency division multiplexing, basically overcomes the inter-symbol interference. Okay. All right. So now once you use OFDM, you can see that the channel coefficients across the subcarriers in the time domain are given by the endpoint FFT, in fact 0 padded FFT of the channel taps in the time domain. That is, the channel coefficients in the frequency domain are given by the FFT of the channel taps, the 0 padded FFT of the channel taps in the time domain. And this is something that we have already seen before. This is given as the channel coefficients. Let me just write it down a bit more clearly. Channel coefficients HL in frequency domain are given by the 0 padded FFT of your channel taps in the time domain. Okay. So, and that is basically can be demonstrated as follows, that is the L channel taps, I pad them. So, these are my L equal to 2 taps, these are the L equal to 2 channel taps, these are the N minus L equals basically 4 minus 2, N equal to 4, L equal to 2 equal to 2 zeros. So, you pad them with, and this is also something that we have seen before, you pad them with N minus L zeros, N equal to 4 point. Now, take your N equal to 4 point FFT, okay, or basically your DFT, your discrete, where DFT basically stands for the discrete Fourier transform. Remember, DFT stands for the DST stands for the discrete Fourier transform, and this yields the channel coefficients across the subcarriers, that is your H0, H1, H2, H3. So, these are the channel taps and these are the time domain, these are the channel taps in the time domain, these are channel coefficients or the subcarrier channel coefficients in the frequency domain, these are the subcarrier channel coefficients in the frequency domain. Therefore, we have the Lth subcarrier coefficient HL is basically given by the FFT as L equal to 0, in fact, this should be k equal to 0, FFT, Lth FFT point of the channel taps Hk e raised to minus j 2 pi KL divided KL divided by n. This is something that we have seen before also. And now, substituting n equal to 4, this is basically k equal to 0, k equal to 0 to 3 Hk e raised to minus j 2 pi KL by 4, which is summation k equal to 0 to 3 Hk e raised to minus j pi by 2 KL. This is basically your capital HL, which is the Lth subcarrier coefficient. This is the Lth subcarrier coefficient. So, capital HL is basically given by the Lth subcarrier coefficient is basically given by the Lth FFT point of the 0 padded channel taps. All right. So, now let us write the explicit expressions for each HL and then we will see something interesting. So, H0 is basically your H of 0 plus H of 1 e power minus j pi by 2 k equal to 0, k equal to 0 and L equal to 0. Yeah. So, that is in fact 0 times 0, or basically k equal to 1, in fact rather k equal to 1 and L equal to 0. So, basically this is H0 plus H1. So, you have capital H0 equals H0 plus H1. you have capital H1 similarly is H0, well H0 plus H1 into e power minus j pi by 2, which is equal to H0 minus j times H1. Similarly, H2, this is equal to H0 plus H1 e power minus j pi, which is equal to H0 minus H1 and capital H3, which is equal to, well, you can check this is H0 plus H1 e power minus j 3 pi by 2 equals H0 plus j H1. And now let us write this all together, write all these channel coefficients across the subcarriers, and what you will find is HC capital H0 equals H0 plus H1, capital H1 equals, well, H0 minus j H1, capital H2 equals H0 minus H1, capital H3 equals H0 plus j H1. And what you realize from this is basically there are only two unknowns, there are only two unknowns. These are your channel taps H0, H1. Yeah. So, out of all these you can realize there are only two, basically only two unknowns. If you view this as a set of equations, basically if you view this as a set of 4 equations in the small h0 and small h1, you realize that basically there are only two unknowns, correct, that is H0, H1. Yeah, basically there are as many unknowns as the channel taps, so capital L equals 2 in this scenario. So, there are two unknowns, and therefore, you only need two equations to estimate the channel taps, which means you need only estimates of two subcarrier channel coefficients to estimate the channel taps H0, H1. That is the point. The point is there are 4 equations and 2 unknowns. There are n equations, basically there are here, there is redundancy because there are n equal to 4 equations, only L equal to 2 unknowns. Therefore, only L equal to 2 pilot symbols are needed. This is in fact a very interesting observation. What we are saying is basically since there are only two unknowns, we need to transmit only two pilot symbols. So, basically there are capital L unknowns where capital L is the number of channel taps. So, you need only capital L pilot symbols, and the rest of the symbols that are loaded onto the subcarriers, remember the capital N minus L symbols can be loaded with capital N minus L subcarriers can be loaded with information symbols, and this is basically the interesting aspect that we are going to explore now. Yeah. So, what I am going to say is basically we need L pilot symbols. So, basically remember we started with capital X0, capital X1, capital X2, capital X3. What are these? These are the n equal to 4 symbols loaded onto your the subcarriers. Previously all these n equal to 4 symbols were pilot symbols. However, now we will only need 2 pilot symbols. So, let us say basically this x1 comma x3 are the L equal to 2 pilot symbols. these are loaded onto subcarriers, basically loaded onto subcarriers 1 and 3, that is small l equal to that is subcarrier 1 comma subcarrier 3. In fact, these subcarriers carrying pilot symbols, these are known as the pilot subcarriers. These are known as the these subcarriers which are loaded with the pilot symbols, these are known as the pilot subcarriers. Okay. So, the rest x0, now these x0, x2, these are not pilot symbols, so these can be, so the rest can be, these are x1 comma x2, these are not your pilot symbols. Well, if these are not pilot symbols, that is corresponding to L equal to I am sorry, these are x equal to 0 comma 2. So, corresponding to subcarrier 0 comma 2, these are not pilot symbols. So, if these are not pilot symbols, then what are these, symbols that are loaded onto subcarrier 0 and 2? These are your regular information symbols, these are the normal information symbols, that is the information bearing symbols. So, these are basically, what are these? These are your regular or your normal information bearing symbols. So, what you are doing is basically, instead of transmitting the pilot symbols on all the subcarriers, you are transmitting pilot symbols on only capital L subcarriers, in this case capital L equals 2, on the rest n minus L, that is, which is 2, again in this case you are transmitting the regular information bearing symbols. So, if you look at the symbols loaded onto the subcarriers, that has the following structure: you have x0, x1, x2, x3. Out of these, your x0, x1, these are your L equal to 2 pilot subcarriers, correct. These are your L equal to 2 pilot subcarriers, and interestingly, these x0, x1, these are the information symbols, these are your L equal to 2, in fact n minus L equal to 2, these are your n minus L information subcarriers. Information subcarriers. So, what we have is basically, we have pilot symbols on the few subcarriers, data symbols or information symbols on the few subcarriers, and these subcarriers are basically meshed, they are arranged like a comb. This is known as a comb type pilot arrangement, basically because not all the subcarriers are carrying pilot symbols, few of them are carrying pilot symbols, that is x1, x3, interspaced or spaced in between them, arranged between them are basically the information subcarriers, that is x0 and x2, and these are basically meshed, arranged like a mesh. This is known as a comb type pilot arrangement. This is like a mesh or like a comb basically, alright. So, this is known as a comb type pilot arrangement. So, such a transmission, this is basically known as your comb type pilot arrangement, or basically you can say comb type pilot transmission. We are going to denote this by this acronym CTP. So, this is basically your CTP pilot transmission or CTP based transmission. Comb type pilot transmission. Okay. And now what we are going to do is, we are going to take these symbols with this comb type pilot transmission, that is the information and pilot symbols, and now we are going to do the, so this is your comb type basically block of symbols, right, and now we are going to do the n equal to, that is the same as before. Now we are going to do the n equal to 4 point IFFT, which is the basically the efficient version of the IDFT, inverse discrete Fourier transform. So, all right. So, this is your comb type symbols, that is comb type block. This is the comb type block. Loaded onto the subcarriers, you generate the samples. Now, you take the n equal to 4 point IFFT and you generate the samples x0, x1, x2, x3. These are generated by the n point IFFT as basically xk equals L equal to 0 to n minus 1, 1 over n, xl e power j 2 pi kl by n. This is the n point IFFT. This is your kth sample, and this is something that you have seen before. This does not change. The only thing that is changed is, now instead of transmitting, the only thing that has changed in this scenario is, instead of loading the pilot symbols onto all the subcarriers, now basically you are loading pilot symbols onto a few subcarriers, data symbols or information symbols onto the rest of the subcarriers, and together with this block, which is comb type block, you take the n equal to 4 point IFFT, or the inverse fast Fourier transform, or basically the IDFT, inverse discrete Fourier transform, to generate the time domain samples. Okay. And once you generate the time domain samples, again the next operation is also similar, is also same, in fact identical, where you basically take x3 from the tail of the block, prefix it at the head. So, basically your next step is again the same thing, that basically you take x3. So, you have x0, x1, x2, x3, and you take x3 from the tail of the block, you prefix this. Of course, we have seen this many times before now. This is known as the cyclic prefix, that is CP, and this thing also remains the same, and this is the block of transmitted symbols with cyclic prefix. This is the block of transmitted symbols with cyclic prefix, something that we already seen before. This block is transmitted across the ISI, that is the ISI channel. This is the transmitted across the your ISI the block of samples transmitted across your ISI channel, basically, which is your yk equals, that is equal to, well, or let me just write it a little bit more clearly, that is yk equals h0 xk plus h1 xk minus 1 plus Vk, and then we have seen many times before that when you transmit this block of samples with the cyclic prefix, the action of the channel in the time domain is basically that of a circular convolution. Therefore, what you get at the output is basically the y, which is equal to y, the received output y is the channel filter H circularly convolved with H in the presence of additive noise V, and this is the key aspect. This is your circular this is the circular convolution. Okay. Now therefore, what this changes is basically in the frequency domain it simply becomes a multiplication, that is once you take the FFT of output, that is FFT of the output symbols, that is y0, that is the received symbols y. In the frequency domain I have YL equals HL times XL plus VL. So, basically this, remember, this is in the frequency domain across each subcarrier L. Now remember, for channel, and here comes the difference between the previous channel estimation scheme and this comb type, that is CTP based channel estimation. Previously we had looked at all the subcarriers because the pilot symbols were transmitted on all the subcarriers. However, in this scheme, remember in CTP pilot symbols are only transmitted on the pilot subcarriers. Therefore, we extract the pilot subcarriers, that is these are the only subcarriers which we are with which we are concerned with regards to channel estimation. So, we extract the pilot subcarriers. Remember, the pilot subcarriers corresponding to small l equal to 1 and small l equal to 3, that is subcarriers 1 and 3 are the pilot subcarriers. So, therefore, you extract the pilot subcarriers. So, in CTP, since pilots are transmitted in CTP, in comb type pilot transmission, CTP, only on L equal to 1, 3 subcarriers, that is basically the pilot subcarriers. So, what we are going to do is we are going to extract the pilot subcarriers. That is corresponding to L equal to 1, 3. And now, once we extract the pilot subcarriers, what you see is basically the corresponding model for the pilot subcarriers is basically Y1 equals H1 times X1 plus V1, Y3 equals X1 X3 plus V3. And remember, these X1 and X3 are your actual transmitted pilot symbols. These X1, X3, these are the transmitted pilot symbols. So, these can now be used for channel estimation, and Y1, Y3, these are the corresponding pilot outputs on the pilot subcarriers. That is important to keep in mind. These are the outputs, but on the pilot subcarriers, these are the corresponding pilot outputs on the pilot subcarriers. Okay. So, what we have, and therefore, these are basically L equal to 1, 3, these are your pilot subcarriers, and that is basically what we can see at this point. All right. So, let us stop this module here. So, what we have seen in this module is basically that we have seen a different kind of pilot transmission strategy, that is the comb type pilot transmission strategy for an OFDM system, where what we are doing is we are not choosing to transmit the pilot symbols on all the subcarriers, rather we have pilot symbols which are loaded onto capital L, that is 2 subcarriers in this scenario, and the rest, that is n minus L subcarriers, are loaded with the regular information symbols. So, now we have a comb type pilot arrangement. You take the FFT of this, the IFFT of this to generate the time domain samples, add the cyclic prefix, now transmit this samples with the cyclic prefix added across the channel. At the receiver, you basically have the received samples. Once you take the FFT at the receiver, you are basically in the, that is in the frequency domain, the output across each subcarrier capital YL, that is the symbol received across each subcarrier capital YL equals HL, the channel coefficient across subcarrier L, times XL, which is the symbol loaded onto subcarrier L, plus VL, which is the noise on the subcarrier L. Now, out of all the subcarriers, remember for channel estimation, we are only interested in the pilot subcarriers. Therefore, we extract the received pilot outputs corresponding to the pilot subcarriers. In this case, the pilot subcarriers are denoted by small l equal to 1 and 3. So, you extract the pilot subcarriers, alright. So, we will stop here and we will continue with this further to look at how the channel is subsequently estimated by extracting these pilot symbols corresponding to the pilot locations or the pilot subcarriers. Thank you very much.